In this video, we're going to put to use the three major laws of logarithms. Let's start with expressing 3 log base 9 of 4 minus log base 9 of 5 as a single logarithm and in a way that shows we didn't need a calculator. Now notice it does not ask us to evaluate this. There's a difference between asking us to evaluate an expression or express it as a single logarithm. The way it's expressed right now, it's expressed as one logarithm minus another. They just want it as a single logarithm, and it goes without saying they want it simplified. So what we're going to do is we're going to recognize that 3 log base 9 of 4 is the same as log base 9 of 4 to the exponent 3. Subtracting log base 9 of 5, we leave that alone. Now 4 to the 3 is equal to 64. So what we've got is the log base 9 of 64 minus the log base 9 of 5. But using the quotient rule of logarithms, we see that the log base 9 of 64 minus the log base 9 of 5, since the bases of the logs are same, we can just express it as the log base 9 of 64 over 5. We haven't evaluated it, so to speak, but we have expressed it as one single logarithm simplified. Well, let's express this now. What we have in this situation is a single logarithm, but now we want to express it in terms of 3 different logarithms, log x, log y, and log z. Okay, well, first thing we'll do is re-express this. Since it's the 8th root of a quantity, we can express that as the quantity raised to the exponent 1/8. Okay, so that's what we do in the first step. Now in the second step, what we do is we take this 1/8 and we move it in front. That's the power law of logarithms. And that gives us this expression here. Now, what we've got now is 1/8 in front, but we can say that the log of this quotient is equal to the log of the numerator minus the log of the denominator. Now, instead of expressing the denominator as the log of y squared z to the 7, we can express this using the sum rule, the product rule, as the log of y squared plus the log of z. So there's a few things going on in this step, but this is what we are able to simplify it to. We're not done, but moving to the next slide, we see that, here we have a little explanation. We need to put the expression from the denominator into brackets when we use the log laws because we're going to be distributing this minus sign shortly. Okay, so we're distributing that minus sign, but also the discussion from earlier holds true that instead of calling this the log of y squared z to the 7, we'll call it the log of y squared plus the log of z to the 7, all in brackets. So now we can take this 3 here, move it in front. We can take this 2 here, move it in front, and take this 7 here and move it in front. That's all due to the power rule of logarithms, and we have this expression right here. But now, to get to the next line, we can distribute that minus sign as you see here. We get this expression. And now what we can do finally is take this 1/8 in front and distribute it to all 3 parts. And we end up with 3/8 log x minus 2/8 log y minus 7/8 log z. But of course, 2/8 can be re-expressed as 1/4. We do that because we're good mathematicians, as it says there. And there's our final answer. Okay, now back to a question more like the first one. Let's express this whole long expression in terms of one logarithm. Now remember what we said ln referred to earlier. It refers to, ln refers to the log base e, where e is roughly equal to 2.718. We don't really need to know that specifically for this question. We just need to keep in mind that when you see ln here, it's just basically a logarithm, and they're all raised to the same base, which opens the door. The logarithms are all to the same base, which opens the door to us being able to use our laws of logarithms. So that's what it says here, and we move on. What we can do is take this 5 and move it up and put it over, raise this whole expression that we're taking the ln of, raise that whole thing to the exponent 5. And that's what we show in this first step. Now, obviously, we're then going to be able to take that 5, and instead of saying a cubed b to the 5, we're going to be able to say a cubed b, a cubed b, a cubed b, a cubed b, a cubed b. And then we're going to be able to multiply those in different orders. So we'll be able to call it a cubed, a cubed, a cubed, a cubed, a cubed, and then b, 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 which is the same as saying a cubed to the exponent 5, b to the exponent 5, which is the same as a to the 15, b to the 5. So this whole expression right here in a moment will be a to the 15, b to the 5. Okay? Now, the point being made here is that this is akin to Bedmas. We deal with the power law of logarithms before the product law. So we're dealing with the exponents before we're dealing with the multiplication or the division. So what we've got here is the ln of a to the 15, b to the 5, plus the ln of c. Well, that'll be the same as the ln of a to the 15, b to the 5, c. We'll be able to multiply these, and that's what we get here. And then when we subtract ln d, we can show that as us dividing by d. And so this is our expression expressing that whole long original expression as one logarithm. Okay, now in this question, what we're going to do is we're going to solve for k, and we're going to show we didn't need a calculator. When you look at this at first, you might be tempted to say, geez, log base 6, I'm not too good at knowing, log base 6 of everything. But this question's a little bit deceptive. You don't really need to be. And we'll show you what we mean as we get into it. Well, first thing we're going to do is we're going to say, okay, like it said on an earlier slide, let's deal with our power laws before we deal with any of the others. So that 3 in front of log base 6 of 2 is going to come up to here, as shown right there. And then we're going to be able to call 2 to the 3. We're going to be able to say that that equals 8. So now we've got log base 6 of 10 plus log base 6 of 8 minus log base 6 of 49, because we were able to take this 2 and move it upstairs like that and call it a 49. Now, when we have all the same bases, and so we're able to use the laws of logarithms we described in an earlier video. The log base 6 of 10 plus the log base 6 of 8 will be the log base 6 of 10 times 8. But don't forget, we're also subtracting the log base 6 of 49, which means we can put that 49 down below. So this whole thing is equal to the log base 6 of 80 over 49. So now, keep in mind what we're saying. The log base 6 of k is equal to all of this. So we're saying the log base 6 of k is equal to the log base 6 of 80 over 49. Well, by observation, you can see we've taken the log base 6 of both sides. So in reality, the argument of these two logarithms must be equal to each other. So we're able to say that k is equal to 80 over 49. And we didn't need a calculator to do it. Okay. Now, in this question, we want to solve for k1, k2, and k3. So this, to me, looks like something that we're going to need to use our laws of logarithms for. So let's get into it. When you see a square root like that, square root of this expression, that just means that the entire expression is being raised to the exponent of 1/2. So that means we can take that 1/2, put it in front, just like we've done here. Now, the log base a of x cubed y squared over w is the same as log base a of x cubed plus log base a of y squared minus log base a of w. This is just a straight application of the product rule and quotient rule of logarithms. What we can do next is we can take the 3, that's the exponent on x right here, and we can move it in front. Take that 2 and move it in front. So we've got 1/2 times 3 log base a of x plus 2 log base a of y minus log base a of w. And now we can distribute in this 1/2. So you'll see what's really key here is keeping your order of operations true. 1/2 times 3 is 3/2. 1/2 times 2 is 1. And 1/2 times -1 is -1/2. And so we're able to say, instead of k1 log base a of x, we're able to say k1 is 3/2. Instead of k2 log base a of y, we're able to say k2 equals 1. And where we see k3 log base a of w, we're able to say that k3 must be equal to -1/2. Now, in this question, we're going to simplify this logarithmic expression, and then we're going to evaluate it. Well, to me, that looks like it might be pretty hard to evaluate because the log base 3 of 6 is not something I know off the top of my head. You know, if you asked me what exponent do I raise 3 to give me 6, I would have no idea. And if you asked me what exponent do I raise 3 to give me 13.5, I would not be able to figure out that exponent either. But maybe the laws of logarithms are going to help us here. Well, what we can do is say that the log base 3 of 6 plus the log base 3 of 13.5 will equal the log base 3 of 6 times 13.5. Okay, so just to really drive it home, the log base 3 of 6 plus the log base 3 of 13.5 will equal the log base 3 of 6 times 13.5. And the reason that works is because we have the same base on these logarithms. Okay, so that's what we do in our first step. Well, 6 times 13.5 is 81. At this point, I'm trying to determine what is the log base 3 of 81. Well, if I said to you the log base 3 of 81 is equal to x, you would say to me, therefore 3 to the x is equal to 81. And you know 81 is equal to 3 to the 4. So you'd be able to say, oh, x must equal 4. In other words, the log base 3 of 81 is equal to 4, as we've shown here. And we've been able to evaluate it without ever resorting to using a calculator. What if we wanted to evaluate this expression? Well, similar to the last one, if you told me 2 raised to some exponent equals 96, I'd tell you I don't know how to evaluate that without a calculator. And if you told me 2 to some exponent is equal to 3, in other words, asking me to find the log base 2 of 3, again, I would say to you, I don't know that answer. But we can use the laws of logarithms to help us evaluate something that seems unevaluatable. The log base 2 of 96 minus the log base 2 of 3 is just going to equal the log base 2 of 96 over 3. Well, 96 over 3 is equal to 32. So now I'm just looking for the log base 2 of 32. Well, if I said to you the log base 2 of 32 is equal to x, you would tell me, therefore, 2 to the x is equal to 32. You know that 32 is equal to 2 to the 5, and you'd tell me that x is therefore equal to 5. And that's our final answer. Okay? What if we want to simplify this expression and then evaluate it? Well, looks kind of tough at first, But when I see the fifth root of 64 written this way, I realize that that's just the same as saying 64 to the exponent 1/5. Now, we're dealing with logarithm to the base of 4 here, so when I see 64, I say to myself, that's just 4 cubed, and again, I'm raising it to the 1/5, and that's just the same as 4 to the 3/5. And when I realize this is what I'm dealing with, the question becomes much easier to evaluate. So the log base 4 of the fifth root of 64 is the same as the log base 4 of 64 to the 1/5. Bringing this 1/5 in front, I can say I've got 1/5 log base 4 of 64. Now I want to evaluate log base 4 of 64. So again, I can say if I let it equal x, that means 4 to the x is equal to 64, which means 4 to the x is equal to 4 cubed, which means x is equal to 3. So I realize the log base 4 of 64 is just 3, and so my answer is 1/5 times 3, which is 3/5. Able to do it without a calculator. If log base b of x is equal to 24, now I want to evaluate the log base b of x to the 4 over the cubed root of x. Okay, well this looks a little different, but let's give it a shot. The log base b of x to the 4 over the cubed root of x is the same as saying the log base b of x to the 4 minus the log base b of the cube root of x. This first part is just a straightforward application of the quotient rule. Now, the cube root of x is the same as x to the exponent 1/3. Okay, so, and then I can take this 4 that's in front and move it down. So I can call this 4 log base b of x. And instead of saying cube root of x, I can call it x to the 1/3. I can bring this down in front, and I can say I've got 4 log base b of x minus 1/3 log base b of x. Well, log base b of x is 24. So I can call this 4 times 24 minus 1/3 times 24, and that'll be something I can evaluate. And the final answer is 88. And I've evaluated it in a way that shows I did not need to use a calculator. Now, suppose here that I'm told if you used your calculator and put in log of 2, you would get an irrational number, infinitely long, non-repeating decimal, but it is approximately equal to 0.3010. The log of 2 is roughly 0.3010, and the log of 3 is roughly 0.4771. So we want you to estimate the log of 24, but don't put log of 24 into your calculator. Use this information. Use the information given and see if you can, the information I'm circling, and see if you can use that to somehow estimate the log of 24. Well, this is how people used to do it in the old days before there were calculators. They had what were called log tables. Well, to do this, what you do is you say 24 is equal to 2 times 2 times 2 times 3, which is 2 cubed times 3. So the log of 24 is the same as the log of 2 cubed times 3. Well, we have a product here, so instead of saying the log of 2 cubed times 3, we can say the log of 2 cubed plus the log of 3. And then we can take this 3 right here, that exponent, we can put it in front. So we've got 3 log 2 plus log 3. Now, the log of 2 is roughly 0.3010, and the log of 3 is roughly 0.4771, and so we end up with 1.3801. And so using the power law and product law of logarithms, we're able to come up with the log of 24. And again, this is something that people had to do a lot of in the old days before calculators had logarithm capabilities. And one more question. Suppose you're told log of 2 is 0.3010 and log of 3 is 0.4771. Use that information to estimate the log of 6 million. Okay, well, In the last question, we said 24 is equal to 2 times 2 times 2 times 3. In other words, we took the base of the we took the argument of the logarithm and we made it into a product using only 2's and 3's. And you might think to yourself, my gosh, do we have to do that with the number 6 million? And the answer is not quite. What we can do instead is realize that 6 million is 2 times 3 times a million, which is 10 to the 6. So the log of 6 million is the log of 2 times 3 times 10 to the 6. Well, that's equal to the log of 2 plus the log of 3 plus the log of 10 to the 6. I can then take that 6 and put it in front, and I've got the log of 2 plus the log of 3 plus 6 times the log of 10. Well, let's think about this for a moment. Log of 10. If I'm asking you for the log of 10, if I say log of 10 equals x, and I'm asking you to solve for x, in other words, what's the log of 10? You realize that the word log on its own means log base 10. So the log base 10 of 10 equals x. Well, that means this 10 raised to this exponent is equal to this 10 right here. Well, that 10 is the same as 10 to the exponent 1. 10 to the x equaling 10 to the 1 tells you x must equal 1. So in other words, the log of 10 is just 1. So we can see where it says log 10, 6 log 10 right there. We can say that's the same as 6 times 1. So what we're really looking at is 0.3010 plus 0.4771 plus 6 times 1. These are both approximate values, so we have to put an approximately symbol here. And the answer is 6.7781. So if you use your calculator to determine the log of 6 million, it'll be roughly 6.7781. Now, one more of these questions. Suppose we've got the same information shown, and we're looking for the log of the fourth root of 0.06. Well, the fourth root of 0.06 is the same as the log of 0.06 to the exponent 1/4. I can move this 1/4 in front, and I've got 1/4 log of 0.06. Now, 0.06 is the same as 6 over 100. So the log of 6 over 100 is the log of 6 minus the log of 100. So if I've got 1/4 in front, I'm doing 1/4 times log 6 minus log 100. Well, the log of 6, again, I want to make it into a combination of log of 2 and log of 3. I know that the log of 6 is equal to the log of 2 times 3, and I know that the log of 100 is equal to the log of 10 squared. So I can now take this 2, move it in front, which is what's shown right here. And instead of saying log of 2 times 3, I can say log of 2 plus log of 3. For the same reason stated on the prior slide, I know that the log of 10 is equal to 1. So this 2 log 10 is really the same as 2 times 1. And log of 2 plus log of 3 is equal to 0.3010 plus 0.4771. And so what I've got is 1/4 times 0.3010 plus 0.4771 minus 2 times 1. And I don't need a calculator's logarithmic capabilities to tell me that the answer there is negative 0.305475. Now, the initial two values of log 2 and log 3 were approximate, so that is just an approximation of the log of the fourth root of 0.06, but it's a pretty good one. In this question here, we want to show we didn't need a calculator. We've got the ln of x cubed equaling 22. Okay, So what we can do here, if we know that the log of x cubed is equal to 22, we know we can put that 3 in front and say 3 ln x is equal to 22. Well, dividing both sides by 3 means the ln of x is equal to 22 over 3. Now, think about what ln of x means. It means the log base e of x is equal to 22 over 3. Well, what that means is the base of the logarithm raised to this number out here is going to equal x. And that's what we've been able to write here. And the thinking is as described above. X equals e to the 22 over 3. Now, clearly you would need a calculator to evaluate that and round it to the nearest decimal, let's say. But you'll see mathematicians leave it as e to the 22 over 3 because e is such an important answer mathematically that rather than round it to 1530.47, we just leave it as e to the 22 over 3. And that's the end of this slideshow on how to use the laws of logarithms in ordinary math questions.